Hello everyone and welcome back to this lecture in the machines lecture series, and this is where we had left off in the previous lecture where we had started discussing what a single phase induction motor was. So I had used this website which I just found on Google, which had this diagram of a single phase induction motor, and in this case specifically a single phase squirrel cage induction motor where the rotor is a squirrel cage, which means it is just a set of bars, rotor bars, which are short circuited on either end. So this is the rotor, and you see these are the bars and these are the short circuits on both ends of the bars, right? The short circuit is necessary so that a current can flow in these bars, and that is essential because only if the current flows will there be a torque which is produced. So this website contains some reasonably interesting information on how it works, right? And as I said, this is the complete circuit of what is inside this. There is a main winding and an auxiliary winding, and as I said, we will first start only with this main winding, and that way we'll build up a use, or rather a reason why we need this auxiliary winding as well, right? So we'll have the main winding and this squirrel cage induction motor. So this is what we're going to start with in this lecture, the actual development of the mathematical model so that we can simulate it. So as always, before starting the lecture, a little bit of brief background that if you're interested in these kind of video lectures but you would like something a little more comprehensive, I do have full-length online courses which you can access on my own website, which is pythonpowerelectronics.com. That is just the name of this project with .com. In this there are a number of buttons that you can check out. There is download, learn, watch and read. If you click on the learn button, this will take you to the list of courses. So you see these are the courses which I have currently, and each one of them you can just click on them to expand. The very first course I have is called Simulating Power Electronic Circuits using Python, and in this I talk about the very basics of how you can use Python to simulate power electronic circuits, and especially how you can use the Python Power Electronics free and open source circuit simulator. The next course I have is Basics of Digital Signal Processing for Power Engineers, and this describes how you can use Python and specifically the signal package within SciPy in order to design and analyze the performance of filters for power electronic applications. And the third course I have is called Simulation of Magnetics for Power Electronics using Python, and in this I talk about how you can simulate magnetic components such as inductors, coupled inductors and transformers using Python and Python Power Electronics. And the fourth course I have is called Control Analysis with Python for Grid Connected Converters, and in this I talk about how you can use Python and the Python control package to design and analyze controllers, and in this case I talk about specifically controllers for power electronic applications with the example of a single phase grid connected converter. And the very last course I have is a free course called Why Specialize in Power Electronics, and this is more of a motivational course for junior undergraduates or even high school students who are trying to decide which domain they should specialize in. So if you're interested, the link for this page is provided in the description of this video, so do check it out if you're interested. So with this, let me return back to the lecture. So as I said, the very first step is we need to start building a mathematical model. And in order to build a mathematical model, we need an equivalent circuit with parameters. So this circuit that you see here is not really an equivalent circuit. This is just a schematic. This shows that we have a single phase voltage source which is applied to the entire induction machine. The induction machine comprises of a main winding and an auxiliary winding, and this is a squirrel cage rotor. So this is not much use for us. We need something a little more detailed. Right? Now, all you have to do is Google the equivalent circuit of an induction motor, right? So if I just click equivalent circuit of an induction motor, you will get this as well, right? And there are many links because this is a very well established topic, so you can always check it out. This is the well established circuit of an induction motor. So let's start building and let's start talking about this. So let me go and actually create this in an Excel sheet to give you a better idea of what I'm trying to do, rather than just look at, let's say, just look at a website. So initially, this of course is just a schematic. This is not really a circuit. We'll be building the circuit later. So of course, initially we have our voltage, so I'll call this VSRC. This is the single phase supply voltage that we are applying to our induction motor. Now, this supply voltage, simply speaking, is applied to the main winding, right? That is what we see here, main winding. Right? And if I go back to this, you see that in this particular circuit, we are applying the voltage to the main winding. Initially, we will not consider the auxiliary winding, right? So if we do consider the main winding, the question is, what is there in this main winding? Now, I would advise you to have a look at this entire page as well as this page, because it tells you a lot about the entire concept of how an induction motor works and also how we come across this circuit. But simply speaking, this main winding will consist of several different components. So I'm just going to delete this, cut this out. So the very first thing you need to understand is, whenever we have a winding, we will have a winding resistance, right? That is absolutely essential. And usually this winding resistance also represents some amount of stray losses in this coil, right? Which is the stator coil. So usually I would just call this RS. RS just means it is a resistance of the stator. That is usually the terminology used. Now, just shrink this a little. Now, once we have RS, the next question is, what else do we have? You could say that we could move this directly and the rest of it is the magnetizing inductance. This is the actual magnetizing inductance, or you could call it the self-inductance of the stator. I'll call this LS, right? So RS, let's call it as the stator inductance, stator resistance, sorry. And LS is the stator inductance. So now the question is, LS is also not a single quantity. LS is also comprised of several others. So the first thing you need to understand is the stator inductance, right? All the current that passes through the stator coil will produce a flux. All of the flux produced by the stator coil is not utilized completely. What that means is, if we go back here and we have a look, and I would say, if you go through this entire working of a single phase induction motor, when current passes through the stator, when we pass an AC current through the stator, it produces a magnetic field. Now this magnetic field is in the air gap of this machine, which means it is in the gap between the rotor and the stator. And this flux associates with the rotor, induces an EMF in it, causes current to flow, and the current that flows produces a flux. These two fluxes, the flux produced by the stator and the flux produced by the rotor, will produce a torque. This torque is very similar to what happens when you move two magnets close to each other, right? If you move two magnets close to each other, right, and if you move the north poles close to each other, they will repel. If you move two opposite poles to each other, like the north pole of one and the south pole of the other, they will attract. Why? Because these are two different magnetic fields and they are interacting. In the same way, you have two different magnetic fields, the magnetic field produced by the stator and the magnetic field produced by the rotor. When they interact, you get a torque. But it's important to understand that all the current that flows through the stator coil will not produce a magnetic field that results in the air gap. Some of it will leak. This is called leakage flux, right? It's simple. It's just like water. All the water that we use is not, or rather we are trying to utilize, some of it will be wasted, right? In exactly the same way, all the flux that is produced is not utilized. Some of it is wasted. And that wastage is denoted by leakage inductance. So let's call this LLS. Alright, so LLS, let me put it here so that I don't have to scroll out. LLS is the leakage inductance of the stator. Okay, is the leakage inductance of the stator. So what that means is this amount of leakage inductance, all the current that flows through this leakage inductance results in a flux that will not produce any useful torque. This is leaked. It is leaked through different avenues, but it just does not associate with the rotor and it does not produce any torque. So now that we've come up here, what exactly this LS is? This LS is no longer the way it was before. We can replace this LS by LM, right? And this LM is the magnetizing inductance of the stator, right? This is the magnetizing inductance. So this leakage inductance is the inductance that results in flux that does not do anything useful. This magnetizing inductance, on the other hand, results in a flux that does useful work, that produces a torque. The flux that is produced because of the current flowing through this inductance associates with the rotor and ends up producing a torque. So now let me actually add another column, probably another one as well, and let me pull this and let me just squeeze this a little. And this is LS. Alright. The reason why I'm doing this is because we would like to, at the same time, it's important to understand that when we have a magnetic field, this magnetic field results in certain losses which are very specific to magnetism. For example, we have eddy current losses. We have hysteresis losses. These losses will result whenever we have a magnetic field, right? So these losses are represented by a core loss component, right? Just could put this, and here I'm going to denote it by RC. So RC I will call as the core loss component, core loss resistance of the stator. Alright, so this is the core loss component. What that means is that when we apply a voltage, right, when we apply a voltage, the current that is produced, that flows through the magnetizing inductance, produces a magnetic field. This magnetic field induces an EMF, and the induced EMF is now responsible for certain losses in the magnetic field, or rather in the magnetic circuit, right? These losses can be in different places. Losses can be in the core, these losses can be in the slots, doesn't really matter, right? Typically these are losses in the core, denoted by core losses and hysteresis losses, and we usually denote it by resistance across the magnetizing inductance, right? So this is the equivalent circuit of the stator. So let's keep going, because what happens is we are talking about an induced EMF, right? I'm just going to stretch it a little and produce this. When this current flows through, and I'm going to remove the short circuit because it's kind of misleading. So let's just remove the short circuit. This voltage, when we apply a single phase voltage, this single phase voltage flows through the circuit, right? There is a resistive drop, there is a leakage drop, and the rest of it flows across the magnetizing inductance. The current that flows through the magnetizing inductance results in a magnetic field. And as I said, the current that flows through this magnetizing inductance produces a magnetic field that is associated with the rotor. Now, always remember, as per Faraday's law, that whenever a current flows through a coil, it produces a magnetic field, and the magnetic field that links with the coil will induce an EMF in that coil itself. Alright, now we will call this E1. That is, this is the induced EMF in the stator coil due to the current flowing through it. Right? So now comes the talk about machines. What about the rotor? The rotor, as we already said, let's go back to this circuit. As we said, the rotor here is mounted within the stator, with an air gap, of course, because only then can it rotate. And due to the flux that is produced in this air gap, there is an induced EMF in the rotor. Right? So there is an induced EMF in the stator. There is also an induced EMF in the rotor. Why? Because remember, this is Faraday's law. When any flux linking with a coil changes, an induced EMF, an EMF is induced in that coil. And the EMF induced in the coil is directly proportional to the rate of change of flux linkage of that coil. These are Faraday's law. Right? So now what that means is there is an induced EMF in the stator. There is also an induced EMF in the rotor. So let's go back to our circuit. What that means is I'm going to give a space, because remember, there is no electrical connection. Right? If you come back here and look, there is no electrical connection between the stator and the rotor. This rotor is mounted within this. It is short circuited on both ends. So there is no wire connection between them. The connection is purely magnetic. Right? So if we come back here and have a look, there we have to give a space. Right? So let me denote it by wire, and then let me pull it. Actually, and let me just change this to ES. Right? So ES is the induced EMF in the stator. So now that we have the induced EMF in the stator, what do we say here? If we denote this empty column by the air gap, what that means is there is an induced EMF in the stator. There will now be an induced EMF in the rotor. Right? So let me call this ER. This is the induced EMF in the rotor. This induced EMF in the rotor is now going to flow through the rotor circuit. Right? Right? Now you could say that there is nothing in the rotor circuit, it's just short circuited bars. But remember, any bar will also have an inductance. Right? Any bar, any wire will have an inductance. So there will be a resistance, there will be an inductance. So we have to model that as well. So I chose the wrong one. Yeah, untitled. So what that means is we are going to repeat part of the circuit. So I'm going to give some space here and exactly the same thing as before. So what that means is there is a rotor inductance and there is a rotor resistance. And let me just close this circuit. There is a rotor resistance. Let me call this RR. So this is the closed path of this rotor. Right? So what that means is, let me just recap. When we apply a voltage source to the stator, a current is going to flow in the stator winding, which is going to produce a flux. And because the voltage applied is an AC voltage, it is a changing current, and therefore the flux produced is also changing. This flux produced, which is changing, is going to induce an EMF in the stator by Faraday's law. And also, because this flux produced is in the air gap, this flux produced is linking not only the stator but also the rotor. And therefore, as per Faraday's law, an induced EMF is also, or rather an EMF is also going to be induced in the rotor. And this induced EMF in the rotor is going to flow, is going to cause a current to flow in the rotor circuit. This current is due to the fact that the rotor consists of bars which are short circuited on either end. It's a squirrel cage rotor. And since these are bars, they will have a they will have an inductance and a resistance. Right? So this is the most simplest form of an induction motor equivalent circuit. Right? Now, as I said, This is just the beginning. I'm going to gradually go into this. So this is not the final circuit. We are going to further simplify the objective. Why am I doing all this? I am doing all this because we want the parameters of these values. We want the parameter of RS, we want the parameter LS, we want LLS, LM, RC, and we even want this LR and IR. So let me just write that down as well. So LR is the rotor inductance and RR is the rotor resistance. Right? We want all these parameters. Because when we have these parameters, and I'll talk about, maybe we'll drop this, we may not need this RC, but we need all the others, right? When we have all these parameters, then we now have a way to represent our equivalent circuit and develop a mathematical model which we can simulate, right? Now, many of you might have used similar equivalent circuit and solved them to actually calculate power or torque or efficiency of induction motors, and those are usually static calculations. What we are going to do is dynamic simulations. So we are going to use these parameters, but we are not going to solve them in the same static way using reactances and using Kirchhoff's voltage law and current law only. We are going to bring in the concept of flux linkages, we are going to bring in the concept of induced EMF, and also we are going to then solve equations iteratively to produce a simulation model. So this lecture has already gotten long enough. I'm going to stop now. In the next lecture, we will continue refining this model a little, right? For now, this is where we will stop. Let me just save this because we can use this in the next one as well. So I'll just put it in simulations and let me create another one. Let me call this basic single phase induction motor, and let me give it a name. The name will be equivalent circuit, and let me just put it also as a CSV file. I don't need to, but it's easier to handle these. And I have saved it. So this is what we're going to use in the next lecture as well, where we start looking at some simplifications and some other assumptions which will help us in developing our simulation model. Because like I said, this is still a little too complex, right? And also we need to have some inferences on each of these parameters that will help us in developing our equations. So with this, I'm going to stop this lecture. If you have any doubts, please do post either in the comments or message me on social media or send me an email, whichever is your preference. Otherwise, I will see you next week. Thank you so much and see you soon. Goodbye for now.